Hello, everyone, and welcome to my presentation. The topic of my presentation is machine learning-based process simulation approach for real-time optimization and active control of composites autoclave processing. First, I'm going to give you an introduction of myself and my co-author. My name is Navid Zubairi. I'm an assistant professor at the Material Science and Engineering Department at the University of Washington. And my co-author is Dr. Keith Dan Humfeld from Boeing Research and Technology. So I'll start by giving you a background on composite manufacturing and process simulation, and then I'll explain how machine learning can be used to develop active controlling of the manufacturing process. If you look at different steps that we have in manufacturing composites and pre-assembly, so if we want to identify key steps, we can say there's a step that we place material, we deposit the material onto tools using methods such as automated fiber placement, AFP. We would then vacuum bag and process them typically for aerospace applications in convective environments such as autoclave or oven. And we control process parameters, including temperature cycle and pressure cycle. Depending of how we place this inside an autoclave at the part, and depending on how the autoclave design we will get different boundary conditions. In this case, heat transfer boundary conditions. You can see an example of airflow inside an autoclave. You can see there's areas with good airflow locations and bad airflow locations. Due to all of these complexities and process parameters that some of them we can control, such as temperature and pressure cycle, some of them we can't control, we will get different levels of manufacturing defects, including undercured parts, overcured parts, macrocracks, porosity, so on and so forth. So it becomes quite important to understand this process before committing to build large parts, and it becomes necessary to do what we call the thermochemical analysis. In this case, you can either use traditional experimental approach by placing thermocouples, do thermal profiling of a part, and look at the temperature history of the part to make sure it is within the bounds and limits that are identified by process specifications. You can also do what is known as process simulation, where you will use things such as finite elements. You simulate the entire part with tools, with the convective boundary conditions around it. And you basically solve the heat transfer equation plus heat generation terms, which is related to heat generation due to polymerization in the part. So it's a complex process. It's also quite lengthy. It takes a long time to set up this problem and solve them. But it's a necessity of the process. You have to do that to make sure that the risk is mitigated. You can also do a simplified version of this. And this becomes quite useful when you are in the early design steps, and you can basically take the 3D problem, do what is known as reduced order modeling, due to the fact that the dominant heat transfer mode is through the thickness of the part. You can take elements, you can take points in the part and tool and do what is known as 1D through thickness or drill through, which is basically a 1D problem of part sitting on a tool, and you have boundary condition, heat transfer boundary condition around it. In this case, you can then solve a simpler heat transfer equation, heat transfer problem. You have one equation that describes heat transfer in the part plus heat generation. You have one equation describing the heat transfer in the tool, and then you have your boundary condition, convective boundary condition, which are controlled by heat transfer coefficient, in this case, H1 and H2. So if the air temperature, for example, is the black line, which is heat up, hold, and cool down, and you look at the temperature at the center of the part, the blue line, and the temperature at the bottom of the tool, you can see that initially they lag behind the air temperature because it takes time for the heat to diffuse to the center of the part and tool. And then you will have a peak, which is even beyond the temperature of the air, and that is due to heat generation in the part, or as it's known as exotherm. So we can do this problem and solve this problem using two main methods, and they each has their own advantages, pros and cons. In the traditional method known as science-based modeling, you can basically characterize boundary condition that you have inside an autoclave. You will get those heat transfer coefficients through different methods. You will characterize material properties, including heat of reaction, for example, using DSC in this case. Once you understand these properties, you can then simulate using finite element simulation. You're basically solving those equations using finite elements. That's science-based modeling. Data-driven modeling or machine learning approach has some parallel to this method, but it's actually quite different in terms of characterization. You start by data, and that data can come from finite element or can come from experiment. Once you have enough data, then you can create in one machine learning approach, it's not the only machine learning approach, in one main branch of machine learning approaches, you can create what is known as surrogate machine learning models, which is similar, let's say like a neural network. It actually works like a finite element model. It can get inputs like a finite element model and can export and give you output like a finite element model with one major difference, and that is it's quite fast. It's extremely faster than traditional finite element models. So it has advantages in developing real-time solutions, as you will see in this study in a few slides from now. So what we've used in this study, we have used a software package developed at the University of Washington called CompML, Composites machine learning software package. It's a framework to develop machine learning models, and you will see how we use it to address specific problems. But it basically has different modules to address thermochemical analysis of composites, process-induced deformation of composites, failure analysis of composites. And if you look at the architecture of this CompML, it has modules to either interact with finite element commercial codes and generate data. It has its own built-in finite element modules to generate data. And then once it's generated enough data, it can train neural networks or other types of machine learning models. And it keeps them inside a basket known as software 2.0. And there is an engine, there is a brain of the operation software 1.0 that can mix and match these trained models to answer specific questions. And again, you will see in a few slides how we will use this software to generate proper machine learning models that can help us to do active control for composite processing. So where do we need to have active control? Why do we even need to have this? And it boils down to this type of problem. You have an autoclave where it's being used to fabricate, process multiple parts at the same time. So you have a rack where you place tools with similar thermal masses, more or less, and that with parts with different geometries sometimes. And as a result, since the load is not known before you start to process the part, before they start going inside an autoclave, it also depends on the technician and people who are loading the autoclave. You will get very different situation if, for example, large parts are placed in front of autoclave or complex parts are placed in front of autoclave. It changes the airflow inside the autoclave. As a result, you will get unknown convective boundary condition in these cases. You wouldn't know what is the boundary conditions before the parts are loaded and before the door is closed and before the airflow starts transferring heat to the part and tool. So in this case, for example, you have multiple parts sitting on multiple tools with unknown boundary conditions. What you do is you will put typically thermocouples under the tools as a proxy to measure the part temperature. And you will look at this data as it comes in to understand what is the part temperature, and you have to show that the part temperature satisfies process specification, as you will see in a second in a demonstration that I have to show how we're using this. So we developed a framework, and the framework was developed to address this specific problem. The problem where we have multiple parts, but we don't know the boundary conditions in them, but we have thermocouple data coming from them. The way this framework works is that thermocouple data from multiple parts comes in at different intervals. For example, every 10 minutes, every 5 minutes, every 15 minutes. There is what we call module 1. This module 1 is a neural network trained by software I just mentioned, that it gets this data and it can give you the boundary condition around these parts. Or multiple boundary condition solution, because this is mathematically it's an ill-posed problem. It will have multiple solutions. It can find all the solutions for all the parts within an autoclave in a very short period of time. The data is then given to what is known an optimizing Q cycle module. It gets those data and it comes up with a cycle, a specific cycle that satisfies process specification in all the parts, but it is also the shortest possible cycle that can do that. So you start with one cycle, in real time you get thermocouple data, and in real time you will come up with an optimized solution to make sure all the parts are cured perfectly. So I'll go through the modules and I'll explain it through the demonstration. It becomes more clear as we go through the demonstration. The first module is basically an extremely fast equivalent of finite element. It's a fast surrogate model. It gets information from multiple parts, their thicknesses, the heat transfer coefficient, known heat transfer coefficient around them. It gets air temperature cycle that you have defined, and it can tell you what is the temperature of the part, what is the temperature of the tool, in the example, as you can see on the right side. It has a specific architecture known as long short-term memory neural network, LSTM. It was trained by CompML by doing 50,000 finite element simulations with the built-in FE module in CompML. And once it saw all the data from these 50,000 simulation, it could recognize patterns in data to basically build this output, which is the part temperature and tool temperature. The major advantage of that over FE is that it's almost 100 times faster than finite element. In this case, each 1D simulation takes around 0.5 seconds. It takes around 2 seconds, and we can do about 50 simulations in 1 second using this module. And you will see later how this can be used to find unknown boundary conditions. The second module takes similar information as the first module. It gets information on boundary conditions, parts, and tool thicknesses from multiple parts, air temperature cycle, and can tell you if these parts pass or fail process specifications. So it's a classifier. It tells you if this air temperature with these many temperatures and thermal stacks are okay to be used inside an autoclave or not. But it's extremely fast. It can do about 30,000 simulations per second. It has a simple architecture known as feed-forward neural network, and it was trained again with the CompML module. Data was generated with the CompML module. And again, I'll explain how they come together to solve a problem that I'll show you in a demonstration in a second. So the demonstration that we have, and I'm going to walk you step by step, is a case where we have 3 parts sitting on 3 tools. And these parts have different thicknesses, tools have different thicknesses. In this case, actually, the tools have the same thickness. The parts are Hexcel AS48552, and the tools are all invert tools. We have 1 thermocouple under each tool. So thermocouple A, B, and C. And we have unknown convective boundary conditions around them. We don't know anything about the boundary conditions. If we knew the boundary conditions, we could calculate, and by the way, these are all subjected to a 1 whole temperature cycle, all of them, as you can see in this example. You will ramp to 180 C, hold for 2 hours, and then cool down. If you knew the boundary conditions, and if you knew the boundary condition, different boundary condition around each part and tool, you would be able to calculate the temperature of the part and tool. This would be temperature at the center of the part and temperature at the bottom of the tool, as you will see in these 3 graphs. In each graph, the red line is the temperature at the bottom of the tool. The blue line is temperature at the center of the part. And you will see different cycles, and you can kind of see that the temperature in the middle one, the B, gets quite high, and it is definitely not satisfying process specification, as you will see in a second, as I'll explain what process specification was used in this case. But these are all unknown at the beginning of the problem. So we wouldn't know at the beginning of the problem if these 3 cases are satisfying specs or not. And we are just getting thermocouple data every 10, 15, 5 minutes as we go through the cycle. 2 process specifications were selected in this demonstration. One is that the part temperature, that's the blue line, the part temperature, the maximum part temperature has to stay below 185 C. In this case, this would be the difference between 180 C, which is the air temperature, and the maximum part temperature as identified here. And this difference has to be less than 5 degrees C. The other one is that the slope, the heating rate of the part, that's the dashed line on the blue line identified in the middle, when the temperature of the air reaches 180 C, has to be between 1 to 3 C per minute. And these are example process specification, but these are typically what you might find in real process specification in terms of temperatures or temperature rates. So in order for an air temperature profile to satisfy process specification, it has to satisfy both of these conditions. So in the first step, we waited for 15 minutes. In the first 15 minutes, thermocouple data from the tool TC came in to the first module of this software. So this software selected a range of potential boundary condition. In this case, 20 to 100 watts per meter square Kelvin, which is typical range for autoclaves. It meshed them into every 5 steps. So that would be 16 different boundary conditions between 20 and 100 watt per meter square Kelvin. For 3 parts and 2 unknowns around 2 unknown boundary conditions around them, you will get 768 cases of potential solutions. Using traditional method, it takes quite a long time to actually match this and run this and see which one matches the first 15 minutes of data. In this case, CompML predicted the solution in all 768 cases, compared them with the first 15 minutes of thermocouple data coming from the bottom of the tool. This entire process took 20 seconds. Out of these 768 cases, it selected 128 potential solution. And these are the solutions that the first 15 minutes of their data temperature is within 1 degree C of the predictions of the machine learning model. And you can see the first 15 minutes is shown, and then you can see the zone that how the predictions is done for beyond 15 minutes. The real solution, the blue one, is within the prediction. So the machine learning module predicts a zone of potential solution beyond 15 minutes. And as you can see, again, it validates that it can do a good job because the real solution lies within that zone. At 30 minutes, this process was repeated. So you wait, this software waited another 15 minutes, repeated the same process. This time, instead of starting with 768 cases, it started with 128 cases from previous step. It did the same analysis on them. It found the zones where all of these solutions, they have similar data in the first 30 minutes of their solution. 58 potential cases were selected. And this entire process took 4 seconds to finish. So at the end of the day, we have 58 potential solutions that represent all 3 parts. So some of them are for part A, some of them part B, some of them for part C. We have more than one solution, again, because we only have 30 minutes of data from the beginning. If we continue this, we will have less and less solution. But at this point, these 58 potential solutions were given to the second module. The second module selected 2,000 potential cure cycles. And this was by varying ramps, holds, adding new holds, changing the time between the holds. So 2,000 cure cycles were created. All of these 58 potential solutions were checked, again, all the 2,000 solutions, all the 2,000 cure cycles. Out of these 2,000 cure cycles, the one that could satisfy process specification in all of these 58 cases were selected. Out of them, the one which was the fastest cure cycle was selected as the optimized cycle. So you can see now that the 1-hole cycle was changed to a 2-hole cycle. This 2-hole cycle is the fastest cycle for which you're satisfying the process specification for all potential solutions by just knowing the first 30 minutes of data. So it's a very robust solution because it's not a unique solution. It assumes the problem has multiple solutions and satisfies all of them. So here's in summary. You start with 1-hole cycle for the 3 parts. You can see that the first cycle was 245 minutes. You can see the max temperature and part heating rate. And this is the maximum temperature, minus 180 C. And you can see that the red areas are the areas that you're not satisfying the specs. So spec 1 was the maximum temperature, spec 2 was on the part heating rate. Then this software converted that into a 2-hole cycle, 327 minutes. The cycle time was extended, but it is the fastest possible solution that can satisfy all process specification in all 3 parts for all potential solution, as you can see. And this entire simulation was done in less than 30 seconds And as you go further and further into the cycle, it becomes even faster and faster. So in conclusion, we've developed a framework that can be used to optimize cure cycles for multiple parts cured in convective environment. This only uses the TC data from the tool, from the bottom of the tool. And this is without any knowledge of convective boundary conditions. And it works based on continuously calculating potential solutions, continuously finding, optimizing the cycle as you go through the cycle. The speed of the framework is such that it can be implemented for real-time optimization of cure cycle. The first step was a 20-second calculation, in this case for 3 parts. And as you do that, repeat that more and more and more, it becomes faster and faster and faster. So by the time you're 20 minutes into the cycle, you're almost real-time calculation in terms of finding the optimized cycle. This potentially can be implemented to basically mitigate the risk associated with unknown boundary conditions, and potentially can basically reduce scrap rate in cases where parts go out of spec. And at the end, I just want to acknowledge the funding from Boeing Company and support and funding from University of Washington. Thank you for your attention.